because I can, equals, okay, now on this side of the equation, I had u times v. I'm just going to leave it like that, u times v. And then minus that other integral was u prime times v, yes? I'm going to write it, but I'm going to do it backwards, v times u prime. We still good? Just rearranging things using the commutative property of multiplication?
The whole time the dx is like...
Yeah, there's dx's at the end of all these. This is more of kind of like a general feel of what's happening. All right, last step, I promise. A slight change in my notation. This is some function u, right? Which was f of x. I'm going to still call it u. But instead of calling that v prime, I'm going to write dv to represent the derivative of v, right? So the derivative of v instead of v prime. Over here, I'm going to write u times v. That's this times this. Minus over here, I'm going to write v. And instead of the derivative of u like this, u prime, I'm going to write du. And what you're looking at there is the formula for integration by parts. And I need to explain what it is and how it works and why it's awesome. But that's the formula. I've derived it for you so you know where it came from. So let's see what this formula actually is saying. That's on your formula sheets, by the way. What formula? I think it's the first one, second one on page 6. Very first one. It's the very first one on your formula sheets. So underneath this, I'm going to remind you kind of what this is saying. This is saying that if you have the integral, wasn't u f of x? U was f of x, right?
Yes.
And then v was g of x, right? And we're taking derivative of it. So g prime of x. And then this integral is with respect to x. So that's this piece. Must be equal to f of x, that's u, times v, which is g of x, minus integral v, which was g of x, times the derivative of u, which is the derivative of the f of x, dx. That's me going back to the other notation with the x's and stuff, f's and g's. This is the way it appears in a book, which is why I wanted to put it down like this. All right, now thinking back to Dr. Richardson, right? What the integration by parts formula is doing is it's saying, hey, let's say you have an integral that you're looking at, all right? And you're having trouble figuring out what to do with it. If you can somehow in that integral see some function f, and then next to it with multiplication, the derivative, not of f, but the derivative of some other function, g. If you see that, this formula allows you to rewrite the problem. It's not going to solve the integral for you. It's just going to allow you to rewrite the problem, and you'll have a new integral. But what's the difference in the new integral? The f here has now become f prime, and the g prime here has now become g. So what you have done is you have transferred the derivative from one function to the other. You have to see an example, all right? But that's the big takeaway from the integration by parts formula. You're transferring the derivative from one piece of the integral to the other. So we're going to have to, when we do a problem with integration by parts, the starting point is to figure out what we're looking at if we can see one piece as some function and then the other piece as the derivative of some function. So we have to actually see that it's the derivative of something. We have to mentally be able to see that. And then ask ourselves, what happens in that new integral? What does that new integral look like? I'm about to do an example. Before I do it, I know some of you have maybe heard this before. There's a way to remember this, a little saying to help you remember that formula. And it's ultraviolet. Is that the right way? Ultraviolet, I think that's right, minus voodoo, V-O-O-D-O-O? Voodoo, is that right? Ultraviolet minus voodoo. I didn't make this up, okay? Someone showed this to me. It's cute. It's, ultraviolet minus voodoo. But you have to remember the integral sign. Take it for what it is. Someone showed it to me. That's the way I remembered it, so. All right, let's go back to that problem we were stuck on. All right, so we have this. We already know there's nothing we can do. Basic U substitution doesn't work, right? So the only other thing I have now is integration by parts, right? So I'm gonna look at this and I'm gonna ask myself, can I look at that expression up there and see some function and then the derivative of some other function?
So some function would be x, and the derivative of the other function would be sine x, or sine x, yeah.
Well, the derivative is cosine x, right? But you're talking about the sine function, right? So one way to look at this, and there are actually two ways to look at it. One way to look at it is that that's the f, right? And then that's the g prime. That's one way to look at it. I'll actually label it that way. One consideration I could have is that this is f of x, and that this right here is the g prime of x. Follow? All right, that's not the only way though. I could have done it reversed, right? I could have said that this is the f of x, right? And then that the x with the dx together, that's my g prime of x, sorry. Could have, right? Is x the derivative of something? What? 1/2 x squared. So yeah, of course I could look at x as the derivative of something. Right? Here, cosine x dx, is that the derivative of something? Yeah, sine, right? So do you all see that there are two different ways I could approach that? Which one is better? Can you do both? Or, yeah, go ahead.
I was going to say doing making x cubed and then the cosine x dx, making that the dt.
Yeah, this right here, right? So, but why though?
Because I think it's...
I mean, why is that the better approach than this approach? You'll have a fraction, yeah? Like the 1/2 x squared thing, yeah? That's something we would want to avoid.
When you think about it, right, so cosine x would be the dv, so then its antiderivative would be just sine x.
Yes?
And the antiderivative of x...
Well, derivative of x.
Yeah, derivative of x would be 1.
1.
So that makes sense.
Okay, so that's the big thing you have to see here, all right? Not necessarily like what would you rather take the derivative or antiderivative of. Dr. Richardson, transferring the derivative, right? Transferring the derivative. You always want to be thinking about this new integral. What is your new integral going to look like? That's what dictates which way you go. What's this going to look like, right? So if I do this, in that new integral, I'm going to see g, not g prime, right? I'm going to see g. What is g? Sine x. I'm going to see f prime. What's f prime? 1. So that new integral is just sine x.
Yeah.
Good. That's what I want. Sine x. That's a nice integral. You see? If you do it this way, though, right? If g prime is x, what's g? 1/2 x squared. And then what's f prime? What's derivative cosine? Negative sine. So your new integral is going to have in it what? 1/2 x squared times negative sine x, which is actually more complicated than the original problem. Do you all see that that would be the case? I'm going to write both. I'm going to go down both roads so you can see it like explicitly in front of you. But when it comes to integration by parts, it is not just like, I'll use whatever. There is a thought process. You pick what is going to work on the other end of the formula. It's not a blind thing. And I know some of you who have seen Cal 2, I know that there are some people, professors, that teach this little thing. I don't even know what it is. It's like, what is it? Yeah, like L-I-A-T-E, Liate or something like that. And it's a thing that helps you like figure out what to choose to be your U, right? Like, what do I, not U, like what's the F, what's the G prime? It's like, you first do L, which is logarithms, then you do I, which is inverses, and then algebraic, and then trig, and then exponential. So it's a way of you just like having a method, which is great. Liate, right? That's great. But for me, I want an engineer who can think about things down the road, which is what integration by parts is about. It's not about first I do logarithms, then I do inverse. It's not that. It's about what is happening down there. What am I going to do here to make what I want happen down there happen? To me, that's just a more valuable thing. I'm not taking a shot at anybody who wants to do Liate or teach it. Great. People teach FOIL all the time, right? I mean, there's cute things we use in math. If you go to a tutor and they say Liate and you're like, what the hell are you talking about? That's what they're talking about, all right? So, all right, let's do it. We're going to start this problem from scratch. We've got about 20 minutes. See what we can do. I want you to see the problem as if I were working it on a piece of paper for the first time, all right? Don't you want someone building a bridge that can... All right, yeah, we might have to take that out. All right, so here's the way we're going to start, at least the way I do it. And like I just said, there's different ways that people teach this. There's like these weird shortcut tables if you have to do integration by parts multiple times. This is the way I do it, all right? I always start, if I know I'm going to do integration by parts, I always start by drawing a table, all right? And in the top left of this table, I put U. In the bottom right, I put dV. Now, I'm going to just put the formula up here so we have it, but it's obviously in your notes as well. That's the integration by parts formula, right? So in the formula, we're starting here, aren't we? We have to choose which function is the f and which one is the derivative of some other function. So I'm going to make the choice right now to let u be the x, and that forces me to use the cosine x dx as the dv, right? That was one of two choices I had. I'm going with this one for right now. Now, whenever I draw my table, the way I work is that the top row are the functions and the bottom row is the derivatives. So if I want to know what the derivative of u is, I differentiate. Anytime I'm working with the table going down, I differentiate. So derivative of u, what's the derivative of u? Or well, what's the derivative of x? 1, but let's put dx, 1 dx. So I differentiated to get here, right? Now here, I need to go back up and figure out what v is. Why do I need du and v? Why do I need those two things? Voodoo, right? I need voodoo, right? I need voodoo. I have udiv. No, there's no thing for that. I have udv, right? I want to know what v du is because that's going to be the new integral. So here I have du. It's just 1 dx. Great. And v I get from this, taking the antiderivative. Antiderivative of that is sine x. Yeah? Before I write the formula out now, before I actually do this, what I like to do is just think about this diagonal right here. I like to think about what that is because that's my new integral, right? That's voodoo right there. So I have sine x and I have 1. And that's going to be in the new integral, and I'm happy, and I'm going to keep moving. All right? So now I'm ready to write this down. This is equal to, according to this formula, u times v. Isn't that just these two multiplied? U times v? Okay. That's x sine x, x times sine x, minus the integral of v du. So v was sine x, and du was 1 dx, right? 1 dx. Do I need the 1? No. I don't need the 1, right? So just dx. See, we have transferred the derivative. We've done something where we took something that was impossible, and by transferring derivative, changing places with the derivative, using a formula, of course. It's not just flipping. There's some other stuff that happens, right? This. But by transferring, I now have a new integral that is much easier to solve. So this now becomes x sine x, nothing changes out there, minus, what is the antiderivative of sine? Negative cosine. Plus c. You see? And that's equal to x sine x plus cosine x plus c. That is the antiderivative. Questions?
How did you come up with this method? Or did you come up with it?
I didn't come up with it. No, I showed you where it came from. It's actually not that crazy, is it, to think about where it came from? Just someone used the product rule and said, hey, let's use this. And what a tool they came up with, right? I actually don't know who came up with it. I don't know if anyone gets credit for it, actually.
It was always Euler.
Yeah, it's probably Euler. Hey, let's check our answer. Yes?
So u is the f of x and dv is the g of x?
Yes. Yep. But almost exclusively in any book or even like differential equations, they're usually going to use u and dv. So we need to get used to that notation. All right, so look, let's check it. I want to make sure that this is, if I take derivative of that, I better get this, right? All right, so how would you do derivative here? You have plus here, don't you? You can do these separately. Let's start with the easier one. Derivative cosine? Negative sine. So I have negative sine x, right? That's this one right here. This one, derivative? Product rule, right? So first derivative of x, which is 1 times sine x, right? Or just sine x. And then plus, now derivative of sine x, cosine x, times the first one, x, right? And we're done? Do you see? Now we're done. Because that's cosine x times x, which is the same as x cosine x. So it works. Somehow the integration by parts like took care of the chain rule and product rule for us. It like did it all. Oh, should we? Yeah, I want to do it. I want to set it up because I want you to see it. Let's say that you came in and you were like, you know what? I don't care. I'm just going to do it whichever way I want. And you set up your u, your dv like this, and you pick the u to be the cosine x instead. And then the dv has to be whatever's left. So if that's cosine x, dv has to be the x dx. dv will always have a dx in it. So will du. You should always have a dx in both of these in this row. All right, so now I'm going to differentiate down. I'm going to integrate up. So du would be negative sine x dx. I'm out of room, sorry. And then what's the antiderivative of x to come back up and get v? 1/2 x squared. Yeah? So do you remember when I said I'm going to look at the diagonal and I'm going to think about that new integral? So I'm thinking to myself, this new integral over here is going to have a 1/2 x squared times a negative sine x dx, right? That's what it's going to have in it. Do you all see that that new integral is worse than the one we started with? Because now you have an x squared in there. Like the 1/2 doesn't matter. The 1/2 could come out, right? So could the negative. So I'm not even really concerned about the half and the negative. Like, forget those for a moment. Just that by itself is worse than this, right? So I don't want to go this way, which is why it's important for you to see the transferring of the derivatives so that you know, kind of see down the road what you're going to be working with, right? Let's do another one. Okay? How about this one? X squared natural log x dx. How are we doing on time? Yeah. Should we first agree that we can't use anything else that we've learned? Like, no basic u substitution? Right? You don't see something in its derivative off by a constant in the numerator, not trapped in none of that stuff from 5.5, right? So, integration by parts is the only other thing you have, right? So let's see here. I'm going to make a table. I need to choose a u and a dv. Think about it for a minute. Raise your hand, and then you can put it right back down. But raise your hand when you think you've figured out what u and dv need to be. Okay? Yes? Yeah, I didn't see you raise your hand.
I have 2 guesses.
You have two. Well, yeah, there's two. You have two. Everyone has 2 options. Everybody has 2 options. But when you think you found the one that's going to be the best, raise your hand. You can put your hand back down after. So I think I've got 2, 3 people, 4 people, 5 people, 6. Got it? Yeah, 7. All right, who wants to tell me what they think it should be and why? Go ahead.
U is going to be natural log of x because du is 1 over x.
So you want to go with natural log of x here because the derivative of that would be 1 over x dx.
Yeah, when you find v and you multiply it through, you're going to be canceling out an x. That's all you're doing.
Okay, so you need to explain that a little bit more. So dv would then be what?
X squared.
X squared dx.
V equals 1/3 x cubed.
V is the antiderivative of that, which is 1/3 x cubed.
So when you multiply those, you get 1/3 x squared.
And when you look at the diagonal of what your new integral is going to include, you can cancel the x's out, right? Like one of the x's will cancel. So really, in the new integral, you're going to have like x squared in there, which is great, right? I like that approach. Now, let's look at the other way. I want everyone to see why the other way doesn't work. If we do x squared here, and we do, what's our option for the other one then? ln x. Then the derivative of this is fine. du is 2x dx, right? But what problem are you going to now run into? What's the antiderivative of the natural log of x? I mean, the derivative is 1 over x, right? But what's the antiderivative?
Isn't it negative 1/2 x to negative 2 now?
Mm-mm. We haven't done it, actually. We don't know what that is. We have no idea what that is, right? Right? We have no idea.